Hey there, guys. How you doing? You like that accent? Well, anyway, pretend you were saying that accent, then you're trying to parallel park a car. I'm sure you've heard of parallel parking before, and that diagram right there, that picture, shows the best parallel park job ever. Except not. It looks like a perpendicular park job. But what we are talking about in this section is exactly that. How can we relate parallel and perpendicular lines? And this is section 3, 4 of our geometry. So, I'm going to jump right in. There are three um, theorems that we're going to add for this chapter, and they have to do with parallel and perpendicular lines. Now, by the way, if you don't remember what perpendicular means, if we have parallel lines, those are lines that never cross. Perpendicular lines would be lines that make right angles. So that's what we're going to compare today. Here are our three theorems. First one, it says, if two lines are parallel to the same line, then they are parallel to each other. Now, this one doesn't have a name. It just says Theorem 3.8. We could say parallel lines theorem. We don't have one of those. So we'll call it the parallel lines theorem. It does say if two lines are parallel to the same line, then they are parallel. So it's kind of like the transitive property of parallel lines. So essentially, we have if A is parallel to B and line B is parallel to C, then we can say that line A is parallel to C as well. All right? Next one we're going to do, Theorem 3.9. If in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this is a little bit different. We're comparing both parallel and perpendicular lines. So we're starting off the first part, the if part. The hypothesis that has to be true if two lines are perpendicular to the same line. So both M and N are perpendicular to line T. That's what's given. Then we can say that they're parallel to each other. And that seems kind of logical, kind of intuitive that that would make sense. So we can prove that M is parallel to N. And the third one, Theorem 3.10, the perpendicular transversal theorem. This one actually has a name. Our theorem says in a plane, here's our if, a line is perpendicular to one of two parallel lines. So we have two parallel lines and we have a line that's perpendicular to the one. Then, so we have N is perpendicular to L and L and M are parallel. Then what can you guess? Well, it's also perpendicular to the other. So it goes right off of our theorem 3.9. And we're going to say that N is also perpendicular to line M. Those are our three theorems we're going to use for today. I want to do some practice with it. I also want to do some proofs. We're going to skip to the practice. It might be in a different order in your notes, but let's take a look at this real quick just to see if we can apply those theorems. So this one says a developer is planning a new housing complex. The map of the complex is shown at the right. Assume that all streets lie in a plane. Okay, it's all a plane there. It says if Washington and Lincoln streets are to be parallel, so if you wanted to draw it out, Washington, Lincoln, okay, that goes there, and they're parallel, they have this arrows. What must be true of angles 1 and 2? Okay, doesn't say anything about how this street relates to it, but what is that true about angles 1 and 2? Well, hopefully you knew that they were supposed to be congruent. Angle 1 is congruent to angle 2. And why is that? That is the corresponding angles theorem. We have two lines parallel and a transversal going through them, then those two angles are congruent. B says which street must be parallel to angles which streets must be parallel if angles 3 and 4 are congruent. So we're saying these two are congruent. So this is also going back to what we learned in the last section. Those are congruent. Those are considered alternate interior angles. If you can look at Jefferson and Washington, and American would be our transversal. So that would be, which streets would be Washington? Would be parallel to, what is that, Jefferson? We got some president name going on here. And that's the alternate interior angles theorem. Alright, now C says if the measure of angle 1 is 90 degrees, so we know this is the right angle, and your answers to part A and B are true, what road, or true, to what roads is Eagle Road perpendicular to? Eagle Road would be perpendicular. If both of those are true, we know these are parallel. And also, this would be parallel to that as well, based on one of our theorems. And it would be perpendicular to all of those. This has to be true. This has to be true. So all three of those, Washington, Lincoln, and Jefferson, would all be perpendicular to it. And not only is it visibly logical to say that, it's also coming from theorems, and those have been proven, so we can use those theorems now. All right, let's get into a couple proofs here. Let's start with this first one. This is actually taking what we have and we're trying to prove theorem 3.9. So it's like we're assuming we don't know anything else up to this point. It says given in a plane R is perpendicular to T and S is perpendicular to T. So that's shown in our picture as well. So let's just say R is perpendicular to T and S is perpendicular to T as well. That's given. Let's try to go off of that and see if we can prove that R, we want to get to R, is parallel to S. Alright, so if let's just go on based on what's given. If they're perpendicular, they're both perpendicular to T, that means that we're going to assume that that's angle 1 and that's angle 2, just so that it makes sense. I know they're going to be congruent because of, which one? Vertical angles, but we're going to label it that way so we know we're dealing with those right angles. So angle 1 and angle 2 are right angles. That's the definition of perpendicular, okay? I'm going right off of that given. Now, based off of that, I'm going to say that angle 1 is congruent to angle 2. We could change it. We could say that they're equal based on the definition of congruence, and then say that substitute it. But we have a theorem. If you go back to chapter 1, there's the right angles theorem. It says that all right angles are congruent to each other. So now we know that angle 1 is congruent to angle 2. Now, based on last section, we already can say this. R is parallel to S. And that would be the converse of the corresponding angles theorem. I don't remember what the number was. I just know it was the converse of the corresponding angles theorem. Because we know that the corresponding angles are congruent. That means those two lines have to be parallel. And that was using the converse of the corresponding angles theorem. So we just proved a theorem that we're going to now use, and it only took us 4 steps to prove it. So I've got another proof for us here. A little bit more of a challenge because we got a lot going on here. But this one says in a plane we're given that C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A. That's all given. And we're ultimately trying to prove that C is perpendicular to A. Okay. So we're trying to prove that C is perpendicular to A. Now C isn't extended. If you extend it, that makes sense. This would be perpendicular, right? But let's just go based off of that perpendicular. And I'm going to label some angles here. We're going to say angle 1, 2, 3. You can do that. We got to have them. We got to talk about them somehow. Based off of the perpendicular, we know that angle 1, angle 2, and angle 3 are all what type of angles? Right angles. And that is our definition of perpendicular lines. Def of perp. Now, if they're all right angles, then they're all equal to each other as well. So angle 1, I'm going to actually... what I'm going to want to do here is add another angle here. I'm going to extend this. We don't know anything about this right now, but I'm going to say it's 4. We're going to need that in a second. Because if you think about it, if we can prove that 4 and 3 are congruent to each other, then by converse of corresponding angles, then C would be parallel to D. Or if we can at least prove that that's a right angle, then we know that those two are perpendicular. So, all right, so based off of that, let's just say that angle 1 is going to be congruent to angle 2, and angle 2 is going to be congruent to angle 3, and that's all from that right angles theorem. We could just say that they're all congruent. But if we know they're all congruent, they're all right angles, we also know that lines A and B, so let's try this. Let's just say line A is parallel to line B, and that would be because of the converse of the corresponding angles theorem. We have to figure out what number that is, so I have to write this down every time. So you know, those are parallel to each other. If those are parallel to each other, and if we extended this, let's just say we have line C as a transversal. That means that angles 1 and 4 are also congruent. Because that would be the corresponding angle theorem. We have parallel lines and a transversal. That would be just the regular corresponding angles theorem. Now, if those are congruent to each other, then, and if we know that angle, then we can also prove that angle 4 is a right angle. So if 1 is congruent to angle 4, and we already said 1 is a right angle, then by the law of detachment, essentially, we're going to be saying that angle 4 is a right angle as well. And I'm going to say the law of detachment for that. You could do it a couple different ways with the law of syllogism, or the transitive property. Or if you wrote it out as equals, change it to equals, we could do stuff with the substitution. But then I can finish it up by saying if those two are congruent, then A, or 4 is a right angle as well, then A and C are perpendicular to each other based on the definition of perpendicular. Smiley face, we did it. Oh, I didn't put a smiley face on the last one. I bet. All right, those are two. The second one was definitely a more challenging proof. First one hopefully made logical sense. That's the kind of stuff we're doing with this, how we can use these theorems, how we can compare right angles, perpendicular lines with parallel lines. So I want to finish it up by having you take a look at these two things. So on your own, I'd like you to find the error, and I'd like you to answer the closing question. And then just to revisit the goal for this section, the goal is to be able to relate parallel and perpendicular lines, and we did that. We got some things, we know the relationship between them. We can also prove things based off of that. So there you go, that's section 3-4. Enjoy the rest of your day.